Hey AP Calc students, more FRQs. This time we're going over AP Calc AB 2012 question number 1. So since it's a question number 1, calculator based, but you can also see at the top here we've got a table of values. So maybe you're getting to the point where you can start predicting some of the ways the question may go. And since it's a table of values but calculator based, it could be a blend of both some approximation methods, but also they give you a function. So we'll see what's going to happen here as we proceed. So the question says, the temperature of the water in a tub at a time t is modeled by a strictly increasing twice differentiable function w, where w of t is measured in degrees Fahrenheit and t is measured in minutes. At time t equals 0, the temperature of the water is 55 degrees Fahrenheit, which is pretty chilly for a tub. The water is being heated for 30 minutes, beginning at t equals 0. Values of w of t, or the temperature of the water, at selected time for the first 20 minutes are given in the table above. Alright, so we have a tub full of water that's fairly cold for bath purposes, and they start heating it up. And so we go from 55 degrees to 71 degrees. And they give us some selected times. Okay? So I think we know what's going on. So since it is a table of values question, let's go ahead and use the strategy of sketching the graph. And we're going from 0 to 20 on time, and pretty short y values of just 55 to 71. So we'll jump up here. And our horizontal axis is time. And let's see, we're going I guess we could probably fit all 20 in here. And I think that's 20 there. And so we have selected values 1, 2, 3, 4. So we have at 0 and at 4 and at 9 and then at 15. So there's 10, 11, 12, 13, 14, 15. And then at the end at 20, 16, 17, 18, 19, 20. Yeah, so we're good there. So those are our selected values, and then we have to go from 55 to 70. Again, scale really doesn't matter here. So we'll start at 55, and we need 4 separate values. So a little bit higher will be 57.1. A little bit higher we'll go 61.8, 67.9, and then our top value will be 71. Alright, looks like we got what we need, and we'll put little points here. So when time begins, the water's 55. 4 minutes later, we've heated up a few degrees. And at 9 minutes, we're at 61.8. And at 15 minutes, we're at 67.9. And then at 20, we are here. Alright, so if we were to sketch that, it's increasing the entire time, it looks like. And that would make sense if you're heating up water consistently. It's not linear, it kind of looks like it could be linear, but it's probably not, but we're increasing the whole time. Alright, so we need there 20 minutes, we're all set, tub of water being heated up, we got it. And again, the function represents the temperature of the water at a given time. Okay, the temperature of the water. Keep that in mind. So let's jump in. A. Use the data to estimate W prime of 12. What do you think the chances are that 12 is right in the middle of an interval? Well, it says estimate. So hopefully you're getting to the point now you represent estimate and you think, oh, it's going to be slope of a secant, average rate of change, algebra 1. So we go to 12, and sure enough, there it is. 9, 10, 11, 12. 12 is right in the middle of the interval here. 3 from 15 and 3 from 9. We're going to use that to estimate the derivative. And we know that the derivative is the slope of a tangent, but we're estimating it with the slope of a secant. Since it's almost looking linear right here, everything would be overlapping on itself anyway. But to be more dramatic, if the function was doing this, and we were estimating that slope of a tangent, we would be using this interval and estimate using the slope of a secant. Better picture, not for what we have. So let's just see. Looks like we need W prime of 12, so let's go on either side of it using AROC. So I'm just going to write AROC there to remind us, and let's see. Let's go back to 9. So when time is 9, our Y value is 61.8. And then let's go to 15, and at 15 we are at 67.9. Alright, so we subtract, and we get a negative 6 on the bottom. And what do we get on top here? We're also negative, right? And we get 67.9 minus 61.8. If you're not, now this is a calculator question, and so if you wanted, you could certainly be throwing this in your calculator, or if you feel like practicing your long subtraction here, you could go 67.9 over 61.8. Or you could do it in your head. Doesn't really matter. We have 1, and we have 6, negative 6.1. And then, if we divide that, you're going to wind up getting, you probably don't want to do or if you have a calculator, you're probably going to take advantage of that. And if you do it in your calculator, you're going to get negative 1.017 rounded. Now, when you do that, just emphasize, for calculator purposes here, when you go negative 6.1 divided by 6, it can be a little bit confusing sometimes when they do and when they don't accept a rounding, and just to keep it consistent, always round to 3 decimal places, even though sometimes you'll see on solutions they'll accept negative 1.016. Well, the next value is 6, and it should round up to a 7. So sometimes it can be confusing as to why they accept a non-rounded or a truncated value and not. So just for consistency, go for the rounding and you'll be fine. But more importantly on this question now is the labeling. So if the function W is the temperature of the water in the tank, the derivative, or the rate of change, because this is approximating instantaneous rate of change with average rate of change, but regardless, we're trying to find the rate of change of the temperature of the water in the tub. So we approximate that the rate the water temperature is changing at time equals 12 is negative 1.017 degrees Fahrenheit per minute. So we could do a degree symbol with an F. So this stands for negative 1.017 degrees Fahrenheit per minute would be our label. Okay? And on the question it says, use correct in units, interpret the meaning of your answer. And so you just want to write down that the rate, the temperature of the water is changing at time equals 12 is approximately, because we did estimate, so is approximately negative 1.017 degrees Fahrenheit per minute. So sometimes you wind up writing the number twice, so that's fine. All right, and there's your 2 points. You get a point for the actual numerical value, but then also the explanation. And in 2020, you'll probably be getting points, additional points for labels, and they'll be allocating more points more than likely. But that's A. Okay, and you've seen this before. Estimate a derivative with average rate of change, slope of a secant. Make sure you get your labels right. Now in this one, you also want to come back to the fact, some of you might be thinking, well, isn't it minutes squared? And the answer is no, because W was not a rate. W was the temperature of the water. W prime is the rate that temperature is changing. This isn't like acceleration, which is a rate of a rate. This is just the rate of the temperature. So it's only one rate, so it's going to be an exponent of just to the first power. B. Use the data in the table to evaluate the integral from 0 to 20 of W prime dt. Use correct units interpreting the meaning of it in the context of this problem. This is a little bit, this is curiously easy, but it's really testing whether you know your notation with the fundamental theorem. Because you guys should be looking at that saying, well, the integral of W prime is just W, just like earlier in the year. gone over several times, when you integrate a derivative, the integral of f prime of x dx, the integral of a derivative is equal to the original function, plus c if it's indefinite. If it was a to b, we would tweak this for the fundamental theorem, and we would say, oh, well, that's going to be f of b minus f of a. So the result of integrating a derivative is getting the original function. Well, they gave us w prime, so if you know the fundamental theorem, this is oddly easy, and then you're second-guessing yourself. Well, following the rules here, this would be the w of 20 minus w of 0. So if you integrate the rate the temperature is changing, you get how much the temperature changed. Well, we actually have these values from the table. From up here, w of 20 is 71 degrees, and w of 0 is 55 degrees. So you're sitting there going, this is weird. Did I do something wrong? Our answer being 16. And so what it says is use the data in the table to evaluate, which we needed to, but we needed to understand the fundamental theorem. Using correct units, explain. Well, this would mean that if you integrate the rate the temperature is changing, this means the temperature changed 16 degrees, but then you got to be precise about your the time measurement. So to just explain this more thoroughly, you would say the meaning of this is the temperature of the water changed 16 degrees Fahrenheit from T equals 0 to T equals 20. If you want to be a little more precise, you could have said from T equals 0 at 55 to T equals 20 at 71, but this is adequate. All right. Part C. For 0 to 20, the average temperature of the water is... Now, what's interesting is they actually give you this in the question, whereas a good question for you would have been, could I figure out the formula for average temperature? Remember, average value of a function. Average value of a function, recall, average value of f is equal to 1 over b minus a times the integral of a to b of f of x dx. Now I'm going to erase this here in just a second, but just to review, average value of a function, 1 over the difference of the interval times the integral over the interval a to b f of x dx. So what they're telling us is that the average value or the average temperature of the water is, and they just replace this with w. And they use, instead of a and b, they use 0 and 20. But it just came from this formula here, average value. So all I'm going to do is rewrite what they gave us here. And they're saying, all right, the average temperature, which should be understandable, is 1/20th, the integral from 0 to 20, of w of t. That would give us the average value. So they're stating that's what it would be. And then they say use a Riemann sum, a left-handed Riemann sum with 4 subintervals indicated by the data in the table to approximate what this value would be. And then there's a little bit more to the question, but let's get to the Riemann sum. Now, hopefully you're getting into a rhythm here with table of values where you were anticipating a Riemann sum of some sort here. And so, sure enough, they ask for it, and they say to come from the left. So in my picture here, I'm going to come from the left, so I'm going to use 0. I'm going to draw vertical lines here at my interval values, which occurred at 0 and 4. I'm going to get rid of this 12 that was used for earlier in the question. And I have 15, and then I have 20. So there's my 4 intervals. Now it says to come from the left, so I'm going to use this 55 height. I'm going to use this 57 here, and there's 61.8, and I use 67.9, and since I'm coming from the left, I never use the last right-hand value, which would be 71. So I'm going to do a little work here, and I'll put the values up here, and then I'll transfer them down here below. So it looks like from this one right here, I'm going to have 4 times the height of 55, plus my next one here, this is going to be 5 times the height I'm going to use is 57.1, plus this distance here is going to be 6, and the height value I'm going to use is 61.8. And then this last one here is 5 times the height value I'm going to use is 67.9. All right, and then you can use your calculator, and that value before you take 1/20th of it is going to be 1,215.8. So all of these added up would be 1,215.8. That is what that total is here. So down here, I'm just going to write this as 1/20th times 1,215.8. And again, with your calculator here, you can just take this, and your final answer divided by 20, or times 1/20th, is going to be 60.79. Okay. So getting back to the beginning part of the question here for part C, they're telling us that this symbol, it gives us the average value of W, which would be the average temperature of the water over the 20-minute interval. So if you think about it, if the water started at 55, or here, started at 55 and warmed up to 71, what was the average temperature of the water in the bath? About 61 degrees. Doesn't sound too outrageous. You know, somewhere in the middle of the interval here, that would have been the average temperature. Okay. And we got that approximation using Riemann sums. Now, the next part of the question, you probably can anticipate now, having done several of these, about is this too high or too low? So let's keep reading. It says, does this approximation overestimate or underestimate the average temperature of the water in these 20 minutes? Explain your reasoning. Well, I think you can clearly see here by our Riemann sum from the left, it's under because the function was increasing. So we're going to say it's an underestimate, and I'll sneak that in here on the very bottom. I'm just going to say underestimate because W is increasing. All right. And you can state also that we're coming from the left. It's not necessary because they're instructing you to come from the left, but if you wanted, you could say underestimate because W is increasing and the Riemann sum was from the left. You could add that. There's part C. All right, now it's time for D. Part D says, for the next 5 minutes, it says for time between 20 and 25, the function that models the water temperature has first derivative given by W prime is equal to 0.4 rad t cosine of 0.06 t. Pretty wacky function. Based on the model, what's the temperature of the water at time equals 25? Well, I'm just going to write down this pretty nutty function here. So they give us W prime is equal to 0.4 rad t times the cosine of 0.06 t. And they say that's the rate of change for the next 5 minutes. And so they want to know what is the temperature at 25. Well, this is a combo question between what we were doing over here. Remember, we integrated a rate and we got the fundamental theorem. This question is basically part B, but it's calculator based instead of table based. So what I'm going to do is they're asking us, what they want to know is, what is W of 25? All right, so here's what we're going to do. We're going to take the 2 intervals, or the 2 interval values. It's 20 to 25. I'm going to set up an integral and use the fundamental theorem, and see if you can anticipate what this is going to have to look like. If I integrate from 20 to 25 minutes of this derivative, which would be W prime of t. Now, make sure you realize notation-wise, I kind of wish on this question they would have changed this to a new value. Sometimes a little confusing because in part D, W is a different function than part A, B, and C. And oftentimes they will just change this to a new letter so there's no confusion, but they didn't on this one. So the integral of W prime of t using the fundamental theorem would be W of 25 minus W of 20. Now what they want to know is what's the temperature of the water at 25. So what we have to do is add the initial condition, which for this part of the question, the initial condition isn't 0. The initial condition for this interval is W of 20. I'm going to take that and add it to the other side. So I would say W of 20 plus the integral from 20 to 25 of W prime of t dt is equal to the temperature of the water at 25. So W of 20, we actually do use when this started, the next part of the interval. It's how warm the water was at the 20th minute, which was the end of the question A through C, and according to the table was 71. So that part is 71 plus, and now it's calculator work. And you have to integrate from 20 to 25, W prime of T dt. And that's going to give us what we need, which would be W of 25. So at this point, calculator time. I think we can put this over here. And we're going to say, I'm going to go ahead and put the 71 in there. We'll put the whole thing on there. 71 plus, I'm going to integrate, and I'm going to go from 20 to 25. Okay, and now I'm going to put in this wacky function here, 0.4 rad t, or x, for our calculator purposes. Cosine, make sure your calculator's in radians, by the way, if you have to do this. And then we have 0.06 x, and our variable of integration is x. Okay, so what we wind up with is a final answer of 73.043 is equal to the temperature at the 25th minute, which seems reasonable. It heated up another couple degrees. So if you wanted, you could have just done this part. In fact, if we just subtract the 71 off of there, the value of this integral was 2.043 degrees. And we added that to 71, and that's what we got. All right. So from the top on this problem here, we have a bath tub filled with water that's needing to be heated up, and it starts at 55 degrees and must have a heating element, or there's a, this is from, I don't know, the hundreds of years ago, and there's a fire underneath this thing, and they're heating it up for some reason. But in 20 minutes, we heat it up 16 degrees. We keep heating up this last part. But what's the average rate of change? They give us an interval. Then find fundamental theorem. Explain what this means. Fundamental theorem, just the water changed 16 degrees. An average rate of change question with a Riemann sum, which is always the case with a table of values. And then they give us the rate of change function. Do we know how to integrate that and polish it off? Okay. So there it is, AP Calc AB 2012 number 1. Thanks.